Hi there, I'm playing with junk again, but I think I should probably rename my channel because all the time I'm playing with nice and expensive stuff that is not really junk, but well, for some people it is, and some people toss it away, but not this time. I have here a HP 5340A frequency counter from the year 1973, 75, about that. And well, a frequency counter in itself is not really something special, but this one can count up to 18 gigahertz. Yes, you heard me right, I said 18 gigahertz. That's what this counter actually can count. Now the question is, how on earth do they do that? I mean, 18 gigahertz, that's not something you just put on a digital counter and count how many waves or impulses there are. They must use some tricks. But before I go to those tricks, I will show you how a frequency counter works anyway. And for that purpose I have another nice device from HP. Maybe I should light it up a little bit so you can better see what it is. It's the 5201L scalar timer. And by the way, it's not 520IL, it's 5201L. So what is a scalar timer? I would rather name it a scalar counter, but they named it a timer. So what it does is this: you attach a scintillator sensor to this input, and the scintillator sensor is basically a large crystal that reacts to gamma radiation, and every time a gamma particle or a gamma quant comes along and hits that crystal, the crystal emits a tiny little bit of light, and that light will be picked up by a photomultiplier tube and creates an electrical impulse that goes in here. So if you want to know what a scintillator is, there are Wikipedia pages about that. The scalar part of this is here. Here you can say what is the minimum amplitude of the pulse that we want to count. We can set here energy minimum and an energy maximum that goes to 10, and you can select the amplitude of pulses you want to count, and this gives you a clue about what radioactive source you have. So different radioactive materials have different strengths of pulses in different energy bands. So you can select a certain band and then count how many times a particle hits. Okay, so let's see what we can do with this one. Okay, then prepare for takeoff. So after hitting the reset button, we are starting at 0, and the noise you probably hear, that's only the fan inside. It seems this is a pretty frequent problem here. I have seen such devices on eBay with the remark loud fan, so it seems that happens quite a lot. On the other side, this device is from 1970, so it's about 50 years old. And I think if only the fan gets a little bit noisy, we can live with that. Good thing is, after a while you can tap at the top of the device and the fan gets much more silent. So I think it's a mechanical issue, and I will care about that a little bit later. Okay, here on this side we can set how many seconds we want to count. It is now on 1, 0, that means 1 second, 0/10 of a second. And my frequency counter is at the moment at 10 kilohertz, so we press the start button and we read 10,000 cycles. In fact, we read 10,004 cycles. Let me repeat that. Now it's 10,005, and the reason for that, I mean, my generator makes exactly 10,000 cycles per second, which is that one here. But the problem here is this unit doesn't have a crystal source for the timer. It takes the mains frequency. And at the moment the mains frequency is a little bit low, so we're reading more pulses than 10,000. And you may probably wonder how I know that the mains frequency is a bit low. Well, of course I could measure the frequency, but there is a website from Swissgrid and you can see at the moment we have 49.97 Hertz. So the clock is ticking a little bit too slow, and that allows us to count some counts more than we actually should. If the frequency is more than 50 Hertz, so 1 second is shorter, and we should count maybe only 9,999 pulses. And as I'm talking here, we are getting closer to 50, so we are only 3 counts off. But the basic problem here is what's the maximum frequency we can actually count. It seems that 10 kilohertz is not a problem for this 50-year-old counter. So let's go to 100 kilohertz and let's see what it does. And it says 140, so 100,040 of course. And we can repeat that, and yes, we are within the specs. By the way, there is a crystal oscillator available for this device, but that's an option that is not installed, and I think it's pretty impossible to find that today. So let's go to 1 megahertz. And now we are facing another problem. We don't have enough digits. So imagine 1,0,0,0,563 Hertz. But there is another trick. We can count only for the 10th of a second. So we get 1 megahertz and a little bit more at the last significant digits. How about 2 megahertz? Yeah, that looks pretty good. How about 5 megahertz? Yes, that still isn't too bad. As I said, that's because of the mains frequency, of course. How about 6? Oh, It crashed again. Yes, 6 looks not too bad. 6 megahertz seems to work. How about 7? Reset, start. Yeah, 7. Still working. How about 8? No. Doesn't even count. Okay. Maybe we should count a little bit longer. No, doesn't want to count. Maybe I have to set that a little bit lower so it counts everything. Oh, now it counts. Okay. Let's do it for a 1/10 of a second. We get 7.98 instead of 8, so I think we are quite a bit more off. How about 9? Oh, 8.6, so we are way off. I think that's not the frequency that thing can count, and it's another number every time. Well, 8.6, but at 5 megahertz it's still working fine. 5000 and a little bit of deviation. And according to the spec sheet, it actually goes up to 5 megahertz. So that's what it does, and it still works perfectly. But the main question is, how do you count 18 gigahertz? That's a nice sound at startup. Let me do that again. But before I'm talking about how this thing works, I have to thank again Adrian from the UK, who sent me these 2 devices here, and he sent them in exchange to a Tektronix RM504 oscilloscope, because he needed that, and by the way, he needs a couple of more of them, because he wants to restore an original Apollo 11 USB console control panel. USB, you probably know that abbreviation, but it means something completely different, because they certainly didn't have USB in the 1970s. USB in that case means Unified S-band communication, or Unified S-band, USB, okay. And that was used to for tracking and communication with the Apollo spacecrafts, from Apollo 6 or 7 up to 17. It was all the same. S-band means a frequency band, which is about 2.5 gigahertz, more or less about that. And well, Andy tries to reconstruct or restore one of these consoles, and for that he needs at least 3. So when I understood him right, 3 of these Tektronix RM504s, and if you have one and you don't need it anymore, you can leave me a note and I will get you the contact of Adrian, and maybe you can make a deal with him. Well, that's about that. But before we go into too much theory, let's have a look inside. That's certainly what you want to see. Isn't that a beauty? It's crammed full with stuff. But there is even more. because there are more modules under this cover here, and you see there is no space wasted. Well, so that's the part where all the magic happens. Here we have our universal input that goes in here, comes up to this power divider that divides the signal into two different directions. One goes into that box here, and the other side goes into that box here, which is more or less identical with some smaller differences. So they call it preamp SC, and I think that's not entirely true, because it's sampler number 1 and sampler number 2. That thing here in the middle, that's the crystal oscillator. It's a ovenized, so it's a heated, controlled temperature crystal oscillator. That's an option, because the original oscillator is just a board that goes in here. That's the board holder here. So they swapped it for a more precise ovenized oscillator. And here in this section you can see the names of the modules here. For example, that's a frequency doubler that makes 20 megahertz out of the 10 megahertz oscillator here. Search, mixer, VCO detector. What is all that? Programmer. Okay, I try to explain that now. Good thing is I also got this original manual here. You can see it's quite a heavy manual with a lot of pages and a lot of schematic fold-out diagrams. And at the moment, since this counter doesn't really work, it doesn't count, so I'm sorry about that. The manual itself is well, it's a joy to sweep through. It starts with the theory of operation, with all the new digital chips that are inside that counter. So they explain every single chip, be it an operational amplifier, be it some decoder here, 10 out of 4 decoder, monostable, multi-vibrator, everything. The only thing they do not explain so exactly is this part here. So they are all go only relatively rough over that. And that's this, the sampling theory. Okay, maybe I have to do my own artwork to explain that, and I try to keep it short because firstly I haven't understood it completely, so I can only tell you what I think I understood correctly. Okay, let's say this is our input frequency we want to measure. When this frequency is lower than 250 megahertz, it is counted directly. So they count 1, 2, 3, 4 and so on waves, and it's displayed, and that's it. So then we have direct count. But when it is more than 250 megahertz, which is already relatively high, they do the sampling method. And that works like that. Let's say you want to measure this frequency here. You could theoretically send it to a super fast switch. Let's say this is our switch, that's the input. Here you go in with the sampling frequency. And what it does is, for that moment when the sampling is on, a short pulse here only, you measure the voltage of this sine wave. So for example, if you sample here, you get that part of the sine wave. If you sample here, you get that part of the sine wave, or maybe that part of the sine wave. Then you feed that in a small capacitor that charges up to that value here, or here, or that value. So here we have, for example, minus 1 volt. Here we have plus 0.7 volt. Here we have plus 0.9 volt, and so on. Now what you could do is to change your sampling frequency from, in the case of this counter here, it's from 100 to 185 megahertz. And you use a ramp impulse like this to go from 100 to 185. If you didn't find anything, you go back and start again. What happens? When you have the right frequency here, you probably hit the 0 point here. 0. And you probably hit the 0 point here, because your frequency, your sampling frequency, is slower than the wave you want to measure. So you probably hit only every 1, 2, 3, 4, 5, 6 zero crossing here. So that means your sampling frequency is n times smaller than the frequency you want to measure, fx, that's the input frequency. So what happens? No matter what frequency you have, you ramp up the sampling frequency here from 100 to 185, which would be at 18 gigahertz exactly, or 18.5 gigahertz. That's megahertz. That's 100 times slower. So that means you sample the maximum frequency with a sampling frequency that is 100 times slower than the 18 gigahertz. You can, if you get 0 here, or at the output of this you also get 0, then you know your input frequency or your sampling frequency is phase locked to the input frequency. Then you keep it in this. And if this is going up or down, plus or minus volt, you can correct your sampling frequency so that you stay at 0 here. I hope that's a little bit understandable how that works. The only problem is you don't know how much n is. So you ramp up this frequency, you get at the point when the output of this sampler here equals 0, then you stop, you keep the frequency, and you know it's probably 150 megahertz. What you don't know is what your input frequency is, because it could be 150 megahertz. That means you're sampling every 0 crossing here. It could also be only 75 megahertz. Then you sample the up and the down slope here of the zero crossing. It could be 300 megahertz. Then you sample here, not here, but here again. And so on up to 18 gigahertz. So that's what sampler number 1 does. It just checks where is my phase lock, where could it be between 100 and 185 megahertz. And the second sampler, which I have shown you in the device, which is almost identical, is there to find out what the factor n is. So how many times is the input signal faster than the sampling? And if you have this number here and n, so what you display is n times f sample equals f unknown. So that's a little bit simplified. Of course, the guys from HP do it a little bit more complicated. They don't look here for a 0 volt, they look here for 20 megahertz. So that's it's basically the same. You just adjust this frequency here so that 20 megahertz come out instead of 0 volt DC. That happens if you, for example, hit this point, then on the next waveform you hit this point, on the next waveform you hit this point, and so on, and that creates you a waveform of 20 megahertz. So if you are off here with the frequency, this 20 megahertz will be lower or higher, and so you just check for 20 megahertz in the same way as you could check for 0 volt DC. Just to explain it, the 0 volt DC sampling here is a little bit easier to understand. Okay, what I did not understand is how they calculate n. So in the second sampler they are using the same sampling frequency, but with an offset of 20 kilohertz, and somehow with some very clever trickery they get an output from this sampler of n times 20 kilohertz. So in the worst case, when we feed in 18 gigahertz, this n will be 100, and that makes it 202 megahertz. Then they feed this frequency to the counter circuit, which computes then, well, the input frequency. Okay, just in case your head is now smoking, I feel exactly the same, because I tried to understand this, and well, it's here in the manual. And maybe I can show you the text so you can read it for yourself. Maybe you're smarter than I am and you're getting it. So that's their diagrams about the sampler. So that's the sampling switch. It's a diode. And as you probably know, every diode needs a certain forward voltage to conduct. So at the standard silicon diode, it's about 0.6, 0.7 volt. And if the input signal is lower than that, it will be blocked. It doesn't conduct. So what they do is, that's the same circuit with two diodes. They feed in here at point A and B a super short pulse, like that. That makes the diode conducting for a very short moment. Then they measure the voltage across this capacitor, and well, that's their sampled voltage. The problem is, if you have to measure 18 gigahertz, you need a super short sampling pulse, and that's the theory about that. So I even don't understand that, because I'm not a high frequency guy. So the idea is you have a cavity where electromagnetic waves can travel, and they feed in the pulse on A and B, and somehow they get the super short pulse. There is another circuit about the sample timing. You see, they only sample every 1, 2, 3, 4th zero crossing, so they have the same example here with the zero crossing, even if the device doesn't use that method. And this is the block diagram of the input stage. We come in here, that's the power divider, that's PLL number 1, that's PLL number 2, or they call it differently. There is the output of 20 megahertz. The generator, they didn't draw that, the sampling generator. And the other one is the N determination circuits. They find out what the factor N is to the sampling frequency they used here to get this 20 megahertz. And all this goes to the counter circuit where the actual frequency is then calculated. So as I said, I would leave this part here untouched, even if it's the most interesting part with all these gold connectors here and all the magic cans inside. But we can have a look at all those smaller boards here. And as you can see, they are completely gold plated, at least on one side. They have a screw to fix it here inside this slot. So when you open the screw, it starts to move and you can remove it. And there is also gold plated PCB tracks. I will install that later. This one is also an interesting board. It has no screws at all, but it has a funny looking chip here. Some golden chips, one even with a heat sink on top. That's all ceramic packages with a golden cover. Maybe we could remove that. Yes. So I have no idea what this is. Probably from the schematic diagram it's some sort of Schmidt trigger. Everything a lot of gold here. Even on this side, I think, even under the silk screen here, no, that's not the silk screen, that's the solder mask. Even underneath that is gold, probably, because they normally put the whole board into a bath to gold plate it, and then they apply the solder mask later. Of course, also the connectors are all gold plated. And the most interesting part, of course, is the Nixie tubes. And that's also the reason why I wanted this, because I told Adrian, send me something with Nixie tubes, and well, that's the two devices he sent me. So the next part will be to try to find why this frequency counter is not counting. And then, well, maybe there is another video with either the device working, or I will take it apart completely. Okay, I think that's enough for today. Thanks for watching.